The main objective of this video is to formally define the network flow problem. To do so, we start by defining what is a network. A network is a directed graph G equal to NA together with some additional numerical information. The first one is the supply. The supply is a real number that we denote by Bi for every node in our directed graph. Then we have the capacity. For every arc in our directed graph, the capacity is a non-negative real number Uij. We also allow Uij to be equal to infinity. Finally, the last numerical information that we need in the definition of a network is the cost per unit of flow. For every arc ij in our directed graph, the cost is a real number Cij. In the following slides, we will use the definition of network together with supply, capacity, and cost per unit of flow to formally define the network flow problem. Let's start by visualizing our directed graph. In our network flow problem, we think of some material that flows on each arc. The amount of flow through an arc ij will be denoted by Fij. Essentially, these will be our variables. So while in the previous chapters we used x to denote our variables, in this chapter we're going to use f because it stands for flow. Next, we discuss the role of the supply. The supply Bi is the amount of flow that enters the network from the outside at node I. Recall that in our definition the supply is a real number, so in particular it can be negative. If it's negative, we have that a negative amount of flow enters the network from the outside. In other words, we have a positive amount of flow that exits the network to the outside. This is why, in this case, the absolute value of Bi is called the demand at node I. Accordingly, a node I is called a source if Bi is positive and a sink if Bi is negative. We are now ready to write down the feasible region of our network flow problem. We have two types of constraints, type 1 and type 2. In the constraints of the first type, we have one equality constraint for every node I in our directed graph. This constraint enforces the flow conservation law. It states that the amount of flow that enters a node I must be equal to the amount of flow that exits the same node. Let's examine this equality constraint more closely. On the left, we have the sum of Fji for every j in delta in of I. So this sum is exactly all the flow that enters node I from inside the network. Then we're adding to this sum the supply Bi. We have just seen that Bi is the amount of flow that enters node I from outside the network. So in total, on the left hand of this equality constraint, we have the total amount of flow that enters node I. On the other hand, on the right hand, we have the sum of Fij for every j in delta out of I. And this is precisely the amount of flow that exits node I while remaining inside of the network. You might be wondering why on the right hand we don't have a quantity symmetric to the Bi on the left hand that represents the amount of flow that exits node I and leaves the network. The reason we don't have such a quantity is that the supply Bi can be either positive or negative. So in this equation, if it's positive, it adds to the sum on the left hand, and if negative, the demand is added to the sum in the right hand. If you remember, we've already seen in chapter 1 some equality constraints that represent the flow conservation law. In fact, we wrote down very similar constraints in the communication network example in chapter 1. Then the second type of constraints is much simpler. These constraints only say that the flow through any arc ij must be non-negative and it cannot exceed the capacity of the arc. Next, we introduce some notation that we're going to use heavily. Every vector with components Fij for every arc ij of our directed graph will be called a flow. If our flow vector also satisfies the constraints 1 and 2, then it will be called a feasible flow. In particular, in this chapter, A feasible flow will correspond to a feasible solution in the previous chapters. Next, we observe that if we sum all the constraints of type 1, then we obtain that the sum of all the supplies is equal to 0. This is very simple to see because essentially the only thing that doesn't cancel out in summing these constraints are the BI. This is because every arc has one head and one tail. So every arc will appear once in a sum of this type and once in a sum of this type, and therefore it will cancel out. So what does it mean that the sum of all the supplies is equal to 0? This means that the total flow from the outside into the network must be equal to the total flow from the network to the outside. From now on, we will always assume that the sum of all the given supplies is equal to 0. The reason we do that is because, as we've just observed, if we don't, then we would have an infeasible problem. Now that we've fully understood the constraints of our network flow problem, we can introduce the objective function. In our objective function, we simply minimize the cost of the flow. Such cost is clearly defined as the sum over all arcs ij in our directed graph of the cost incurred on that arc. Such a cost is just the product of the unit cost on that arc times the flow on that arc. From now on, the problem of minimizing this objective function over all the constraints of type 1 and type 2 will be called the minimum cost network flow problem. It is immediate to see that such a problem is a linear programming problem. Since all the functions that appear in the definition of such a problem are linear in F, we obtain that our minimum cost network flow problem is a linear programming problem. A special case that we will be considering is when all the capacities are equal to infinity. In this case, we say that the problem is uncapacitated. Otherwise, the problem is said to be capacitated. The uncapacitated case is especially interesting for us because it results in a linear programming problem in standard form. In fact, if all the capacities are infinity, we can throw away the constraints that Fij is less than or equal to Uij. In this case, we're only left with the quality constraints and with all non-negative variables. Next, we're gonna see how we can formulate concisely our network flow problem by using incidence matrices of directed graphs. As we will always do, we assume that our set of nodes is the set 1, 2, 3 until n. Furthermore, the number of arcs will be m. Now we want to obtain a vector f that contains all the flows of the arcs Fij. Of course, to do that, we need to fix a particular orderings of the arcs, so that we know which arc corresponds to the first component, which one to the second, and so on and so forth. At this point, we are ready to define the node arc incidence matrix A of our directed graph. The dimension of our matrix A is n times m. In particular, every row corresponds to a node, and every column corresponds to an arc. To define the matrix A, I only need to define a general entry aik, where I is the ith node and k is the kth arc. This is the entry in row I and column k, so it will be associated with the ith node and with the kth arc in the ordering that we have just fixed. Aik is defined as follows. It is equal to 1 if I is the tail of the kth arc. It is minus 1 if I is the head of the kth arc, and it's 0 otherwise. So the structure of A is very simple if we look separately at the columns of A. In fact, every column of A corresponds to an arc, so it will have exactly two non-zero entries, one equal to plus 1 and one equal to minus 1. The entry equal to 1 will be in the row corresponding to the tail of the arc, and the entry equal to minus 1 will be in the row corresponding to the head of the arc. Let's immediately see an example. We have a picture here of a directed graph, and we select the following ordering of arcs: 1, 2, 2, 1, 3, 2, 4, 3, 1, 4, 1, 3, and 3, 5. Let me remark that you can pick any ordering that you like. Everything you need to do is to be consistent and always use the same ordering for the vector f and for the columns of A. Now with this ordering, we obtain this node arc incidence matrix. As you can see, in red I've indexed the rows and the columns. The rows are indexed with the nodes. Our nodes are 1, 2, 3, 4, 5, and accordingly I have 1, 2, 3, 4, 5. The columns instead are indexed using the arcs, and I'm gonna follow exactly the ordering that I've just fixed. So I have 1, 2, 2, 1, 3, 2, 4, 3, 1, 4, 1, 3, and 3, 5. Now let's look at the first column of A. It corresponds to arc 1, 2, so I will have a +1 for the node 1 and a -1 for node 2. We can then look at the second column. This corresponds to the arc 2, 1. I will have a +1 corresponding to node 2 and a -1 corresponding to node 1. And so on and so forth. The same rule applies to all the other columns. So we have understood very well how this matrix looks like if we look separately at its columns. Now what happens instead if we look at its rows? Let's look for example at the first row, which corresponds to node 1. I have a 1 in the columns corresponding to the arcs 1, 2, 1, 4, and 1, 3. And I have a -1 corresponding to the arc 2, 1. So I have a +1 in the columns corresponding to the arcs leaving node 1, and I have a -1 in the columns corresponding to the arcs entering node 1. And this is exactly the general rule that applies to every row of our node arc incidence matrix. This understanding allows us to write in a compact form the quantity sum of Fij for every j in delta out of I minus the sum of Fji for every j in delta in of I. In fact, this quantity is simply the scalar product Ai transposed F, where Ai is the ith row of our node arc incidence matrix. Now, being able to write down in a compact way this difference of sums allows us to write in a compact form the flow conservation constraint at node I. In fact, we can bring the first sum to the right, and our equality constraint can then be written as AI transpose F is equal to BI. In turn, this allows us to write in a compact form all the flow conservation constraints. In fact, they can simply be written as AF equal to B, where once again A is our node arc incidence matrix and B is the vector of supplies B1 until Bn. In particular, A is the constraint matrix of our linear programming problem in standard form. We immediately observe that the sum of the rows of A is equal to the zero vector. This is immediate to realize because every column contains 1 plus 1 and 1 minus 1. However, this is bad news because this means that the rows of A are linearly dependent. And so our matrix A violates one of the basic assumptions in our development of the simplex method. Back in chapter 2, we discussed this possibility, and we saw that in this case either the problem is infeasible or we can remove some of the equality constraints without affecting the feasible set. Removing these equality constraints allows us to be left with constraints that are linearly independent. Next, we discuss a very special type of flows that are called circulations. In particular, circulations will be extremely useful in the network simplex, and they are also useful for other types of combinatorial algorithms for network flow problems. A circulation is defined as a flow vector f that satisfies AF equal to 0. Note that a circulation is a flow vector that is not necessarily feasible. Now, asking for AF equal to 0 essentially means that all our supplies are set to 0. Intuitively, this means that there is no flow coming into the network from the outside and no flow going from the network to the outside. So essentially the flow just circulates inside the network, and this is why we use the word circulation. Next, we will define a very special type of circulation that is called a simple circulation. To construct that, we start from a cycle C. Here we have an example where the cycle is given by node sequence 1, 2, 3, 4, 5, 1, and the associated arc sequence is given by 1, 2, 2, 3, 4, 3, 4, 5, and 1, 5. Now we partition the arcs in the cycle into the sets F and B. F stands for forward, and it contains all the arcs that are forwards in the cycle. In our example above, F contains 1, 2, 2, 3, and 4, 5. The other set in our partition is B for backwards, and of course it contains all the arcs that are backwards arcs in the cycle. In our example, these are the arcs 4, 3 and 1, 5. Now we are ready to define the simple circulation associated with the cycle C. This simple circulation is denoted by hc and is defined as follows. The component of hc corresponding to the arc ij is equal to 1 if ij is in F, it is equal to -1 if ij is in B, and it is 0 otherwise. So in our example, we have a 1, 1, -1, 1, and -1. All the remaining arcs in the directed graph have value 0 in the simple circulation. The first thing that we should check is that our simple circulation deserves such a name. So we need to check that it is indeed a circulation. In fact, it is, because it satisfies AHC equal to 0. Now let's see why these constraints indeed hold. For every node in our cycle, there are 2 consecutive arcs on the cycle that contain it. For example, for node 2, we have arc 1, 2 and arc 2, 3. Now we look at the orientation of these 2 arcs. There are only 2 cases. Either the 2 arcs are oriented in the same way, as it happens for node 2 in our cycle here, or they have the opposite orientation, as it happens for the node 3 in our cycle. Now we study separately these 2 cases. Now let's consider the first case where the 2 arcs are oriented in the same way. These 2 arcs carry the same amount of flow, but one of them enters and one of them leaves the node we are considering. Therefore, the amount of flow that enters is equal to the amount of flow that leaves, and our flow conservation is satisfied at that node. Now the other case is when 2 consecutive arcs have the opposite orientation. In this case, the flow carried by the 2 arcs is opposite, and so it sums to 0. So also in this case, the flow conservation on that node is satisfied. Now that we've analyzed these 2 possible cases, we have shown that AI transposed HC is equal to 0 for every node I. Therefore, AHC is equal to 0, and HC is indeed a circulation. Now, why are we interested in simple circulations? In many algorithms, simple circulations are used to modify a flow vector. So suppose that you already have a flow vector f and you have a cycle C, then you can consider f plus theta times hc, where theta is any scalar. This new flow is said to be obtained from f by pushing theta units of flow around the cycle C. The reason why we consider this new flow vector f plus theta hc is that if f satisfies the flow conservation constraints, then so does the new flow. This is very simple to check. Everything we need to do is check that A times the new flow is equal to B. We start by expanding the product, and so we write AF plus theta times AHC. Now, since HC is a circulation, we have AHC equal to 0, so this is equal to B plus 0, which is equal to B. So at this point it's clear that simple circulations can be used to modify our flow vector. The next question is what is the cost change from the old flow to the new flow? We can simply calculate this cost change. This is C transposed, the new flow, minus C transposed, the original flow F. Again, we expand and we will see that C transpose F simplifies and we're left with theta times C transposed HC. So the resulting cost change is theta times C transposed HC. So this quantity C transpose HC plays a fundamental role for us. and we're gonna call it the cost of the cycle. Formally, the cost of a cycle C is C transposed HC. Of course, we can also expand C transposed HC using the definition of HC. We obtain that the cost of a cycle C is equal to the sum of Cij over all arcs ij that are forward in the cycle C minus the sum of Cij for all the arcs ij that are backwards in the cycle C. And this concludes our video on the formulation of the network flow problem. The next time we will see the network simplex algorithm.